tell you, it's a bit of a tough talk. It's not the chemistry. This is an emotional moment. Many of us, as former students of Harry Wasserman, have come from great distances to be here to celebrate this very special person. And I assure you, as Scott suggested, the organizers are extremely appreciative to everyone who's come here today. Now, Harry Wasserman, he taught us, of course, as students, a lot of chemistry. But it wasn't the chemistry that I think we're here today. In my opinion, it's the other stuff. It's the intangible stuff. It's the lifelong lessons that he taught us that were so special for being part of the Wasserman group. Now, as students, especially graduate students, I happened to arrive in the fall of 1973. And at the time, we were incredibly busy that first year. As first-year students, we were taking lab classes, organic classes from Martin Saunders. We were taking quantum mechanics just in the first semester. Second semester, God help us, we had Fred Ziegler's class in synthesis. And two different foreign languages. But when we finally got through to the end, as graduate students, it was time to go shopping for a PhD mentor. Now, I don't know how or why I had the chutzpah to go up to Harry Wasserman. And I said to him, so, if I join your group, what kind of a chemist am I going to be? Well, he looked at me, taken a little bit back, and said, well, we're going to study the chemistry of reactive intermediates, simple oxygen, cyclopropanone. And we're going to use these in synthesis. So I listened to what he had to say. I liked him. I said, I'm in. And as a graduate student, as many of you know, we did what we had to do to get through, to get our degrees. But again, we're not here to talk about the specifics of the chemistry. It's those special moments. Now, I don't know about you. Let me give you a for instance. I'm in my lab. In walks Harry Wasserman, coat and a briefcase. He puts the briefcase on the table, which doesn't exist anymore, obviously declined, unfortunately. He opens it up, and he says to me, I'm on a train in an hour. I'm heading down to Philadelphia. I'm going to spend tomorrow as a consultant at SKF, the old Smith Klein in French. I need to get some ideas for research. So he walks over to my desk, and he takes one issue of JACS, this thick, puts it in his desk, and in his briefcase, he folds it, he walks out and says, I'll see you tomorrow night. And I'm standing there. Are you kidding me? You take one issue of a journal, JACS, even today, it doesn't have very much organic chemistry, maybe a few communications at the end. He's going to get ideas from one issue. Next day, 10 o'clock at night, walks into the lab, gives me the issue back. Says, I got fantastic ideas. Be in my office tomorrow morning. Let's discuss it. I go into his office, and there he is, a Woodward student, at the board. Beautiful chalkwork, expanding on all the things that he'd taken on. He taught me how to appreciate the literature, how to read, how to stay on top of things, how to get ideas and develop chemistry. Now, of course, it was Harry Wasserman, the instructor, Yale's award-winning educator. I had the privilege, perhaps you did too, of watching this guy walk through the crowd. He had a style where he, because he was on a wireless mic, he knew that he was going to endear himself to his audience. He would go into the crowd and find an open seat as he would lecture to sophomore organic chemistry. sit next to individual students, talk one-on-one, because the chemistry was at the blackboard. The chemistry was on the slide. People didn't have to look at him. But he taught me how to be an effective communicator, how to become one and appreciate the audience, and to communicate to the people he's trying to get his science to. Now, there was also Harry Wasserman, the artist, the musician. For me, I still don't. I have absolutely no talent in these areas. But I could watch him. I could appreciate the way he brought aesthetics to, for example, the journals. No paper went into tetrahedron letters unless the science was good and the quality of the artwork was there. He taught me to appreciate the world around us, the beauty associated with just the arts. And so, isn't it interesting that now my career has taken a turn? In fact, we are now very much aware of our environment. And it turns out that as a traditional organic chemist, trained by Harry Wasserman, trained by E.J. Corey, and making it through Fred Ziegler's class, we now, right, are looking towards ways as organic chemists to pay attention to what we as a group are doing to our environment. And I would argue, as perhaps the title suggests, that the way in which we do chemistry today is simply not sustainable. And I bring that up within the context of the way that we go about doing chemistry. We do chemistry in organic solids. And I, for one, cannot understand what is the evolution of organic chemistry that uses organic solids. Now you're saying to yourself, well, what does that mean? Obviously, we need organic solids. We have to do chemistry in something where things are soluble. Excuse me, but I would argue and question that because, you know, when was the last time that nature ran a reaction in THF? How is it possible, whatever the history is of the use of organic solvents, and nobody seems to know that history. We understand the history of organic synthesis, but what's the history of the use of organic solvents? We had brilliant chemists back then. Why did they not appreciate that nature has been doing chemistry for billions of years and does it under very mild conditions? It does it in water. Do we not appreciate that the solvent issue, which is 85% of the organic waste created by the chemical enterprise worldwide, where's it going? I bet here, for any organic student, when you run your reactions and you create your organic waste, you put it in your tubs, and somebody comes along, maybe once a week, and you're thrilled that somebody gets it out of your lab. Where does it go? Do they burn it? Well, that's not helping climate change. Do they bury it in some godforsaken place in Utah? And we all hope that in 100 years, it doesn't come back to haunt us. It doesn't get into our water. Is that the right way to do it? Well, part of that relationship with Harry Wasserman lasted for decades. Because he was associated with, for example, Tetrahedron Symposium and print, he came to students, such as myself, and said, well, what kinds of ideas do you have? One of which, for example, was in copper chemistry. I was guest editor for Symposium and print on copper. What about nickel? We do that. Would you like to do it? Sure. We did that. But then in 2010, together with Yale's Paul Monastis, we put out the first symposium in print in green chemistry. And our contribution, again, was to focus on ways, and still is, of getting organic solvents out of organic reactions. And so a couple of quick stories that I would like to share with you, all unpublished work, right, is in that vein. So in the Harry Wasserman tradition, then, in my opinion, this story is about vision. He had it. He taught it to us. And the vision today for organic chemists is very simple. Every student who walks into a lab every single day is faced with a very simple question. Which organic solvent shall I use today for my reaction? But I would argue that with vision, one can look into the future. And what I'm anticipating is that the day will come that the organic student will walk into the lab and there will be one bottle on the shelf. And it will be a bottle of water. But in that bottle of water will be a little magic. And that combination will enable you to run your reactions with your water-insoluble substrates, your water-insoluble catalysts, and there'll be a bonus. You won't have to invest any energy into your chemistry. No heating, no cooling, beyond that provided by room temperature. So, in the words of Roger Sheldon, we all can appreciate that we would like to be able to do chemistry in the absence of any solvent. Because you see, in the Paul Anastas sense and the John Warner sense, who wrote the 12 principles, we're not looking to solve the problem by taking the waste and figuring out what to do with it. The 12 principles teach us, don't create it. Don't create the waste. In this case, the elephant in the room is organic solvent. But we need something. We need some medium to do our chemistry. Especially if it's at room temperature, we can't do our chemistry in water as a solvent. Because we can't change the fundamental principles of our substrates and our catalysts. So what we have done, therefore, everyone's heard of the so-called alternative reaction media. And as important as all of these are, clearly the one that has the most logical generality is going to be water, but it can't really be the solvent. So the key word is medium, the reaction medium. But at room temperature, nothing's soluble. So what are we going to do? We're going to take from the traditional side the concept of some type of organic solvent, quote unquote, and we're going to form what we would consider a new world. And yes, just as Fred Ziegler told me years ago, what do you mean, your own world? Yes, today that has come true. We are essentially in our own world. Because we're not here in water as a solvent, and we're certainly not here in the traditional sense. But how are we going to do this chemistry if nothing's soluble in water at room temperature? So for this, we need to step back a moment and talk about soap. It comes in all shapes and sizes. So, you got a problem with that? Right? So, look, we all understand, I think, that soap, for example, here, we could go down the block into downtown New Haven, and we can buy soap. Everybody can go into a store and buy a cheap bar of ivory soap. Or you can go to Provence. Smell it. Lemongrass. What do you think? Smells good? Give it back. Right? So they're not all the same. And when we think about soap and detergents and emulsifying agents and the like, right? What do we know about these? Well, they've been around for a long time. And if we're interested in using a surfactant, for example, to help solubilize our water-insoluble substrates in water at room temperature, where did they come from? If you open up your old catalog, you can buy these things. Where did they come from? Micellar catalysis, the concept's been around for 100 years. Well, the answer is from industries that were interested in solubilizing or mixing oil with water. How many of you think that in these industries there was a synthetic organic chemist developing a surfactant to do sophisticated palladium catalyzed cross-coupling reactions? Raise your hand. No, of course not. Of Of course not. But isn't it time, since all soaps are different, isn't it time that we did that? And so we have created what we would call designer surfactants. They're surfactants by organic chemists that work for the kinds of chemistry that we actually want to do. And as you can see, in the anastas and water sense, they're absolutely benign. In fact, and I don't recommend this, but if you ran your reaction in the minimum of this, which we use 2 weight percent, so there's hardly any of it there, in just water, at room temperature, and you pulled everything out, you could drink it. Because it's nothing more than ester E, vitamin E. Right? The ester E is the acetate that you would buy vitamin E. These are unsymmetrical diesters, and every component is grass-firm, meaning generally recognized as safe. You can literally take every one of these and drink it. And you'll be getting your vitamin E, or in the case of our 3rd generation, notice that this is based on just a phytosterol. You pay to have this sprinkled on your beans. Right? It's a cholesterol-lowering mimic due to that ethyl group there in cholesterol. So all of these are environmentally benign. This is what we're going to use by dissolution in water. Spontaneously, they form nanoparticles, and yes, the grease, the vitamin E, associates, goes on the inside, and that's going to be our solvent. Strangely enough, you're thinking, well, what do you mean, vitamin E is my solvent? Are you crazy? Come on, there's hardly any of this in there. 2 weight percent, which means it's about 10 to the minus 2 molar. Right? So there's hardly any in there. 98% of the medium is water. No organic solvent. But everything wants in there because that is the solvent. That's where the chemistry is going to happen. So we have developed what today the technology and the wording would be a library of all these different kinds of reactions. But notice they're all taking place under the same conditions, the same type of surfactant, in water, room temperature. When you run reactions, if you do this one or this one or this one, you change your solvents. You don't have to do that. So we get to do all kinds of interesting things like chain reactions because it's all happening in the same reaction medium. We can even do things that are technically impossible. Every textbook will tell you you can't do Nagisa couplings in water sense. The same reagents in water. Yes, you can. You can't do copper chemistry in water. Yes, you can. It's a new world, a totally different world where the rules are different. So here's the situation. We put the surfactant into water. Can't make a mistake. Self-organizes, and it's a dynamic system. And that means that on roughly the NMR timescale, you have exchange between everything. The individual molecules, and maybe there are, let's say, 75 to 100 of them per nanoparticle. Your substrates, everything is exchanging. Quite frankly, it's promiscuous. They're going between nanoparticles left and right through the water, exchanging. Same for your substrates, same for your catalysts, same for your products. So, at any given time, could be missing 50%, 20%. It's very easy to get things in, very easy to get things out. No problem. You don't lose the molecule of product. Now, what about gases? Gases now. Hydrogenation chemistry, for example. If there was hydrogen in the pot, it has 2 choices. Does it stay in the water, or does it actually go inside the nanoparticle where the hydrocarbon is associated with the side chain of vitamin E? Well, the fact of the matter is all that data is already known, and it's very clear for hydrogen that relative to water, hydrogen is much more soluble in hydrocarbon. So what that suggests, therefore, is that if we go to generate a reaction containing hydrogen in the medium, most of it's going to be exactly where our substrate and catalysts are inside the nanoparticle. We should be able to take advantage of that. So let's take a look at something that I'm sure Harry Wasserman taught every sophomore organic class. The fundamental reaction of a Lenoir reduction. Everyone here who's taken organic chemistry knows that when you take this unsymmetrical or even symmetrical disubstituted alkyne, use this heterogeneous palladium on, let's say, calcium carbonate, add your poisons such as quinoline, you can anticipate a very clean and selective reduction to the corresponding Z alkene. So here's the question. If you had a 25-step total synthesis, would you trust your molecule at step 20 to a Lin-Law reduction? Well, you don't have to answer the question because the literature has done that for us. The fact of the matter is, there's an entire review that asks that question. Right? Would you really do that in a functionalized molecule? There must be a good reason it's asking the question, because the answer is no. Why not? Because there are problems with Lin-Law reductions. Easy isomerization, loss of material on workup, consistency between material from vendor to vendor. And so, suffice it to say that if you look over the past 4 or 5, 7 years, you're going to find chemistry from palladium, from copper, from gold, from ruthenium, from iridium. Why? Because there's no general method to do it. And if you ask the question, well, what about green chemistry? Is there an environmentally benign way to do that? No. So what would Harry Wasserman say about all this? Well, here's a lesson that I learned from Harry Wasserman many times. Because you see, he would tell us, to get ideas, ideas are cheap. But you have to be ready when a good idea comes along to recognize it and to go after it. And I've never forgotten that. And he said, take notes, go to seminars, read the literature, because you never know when you're going to be in position to pursue those ideas. And so, in fact, while a beginning second-year student, here's my book, dated 1974, $1.35. That's all it cost. But I still have it. He taught me how to think about things and to identify good ideas. So let me suggest to you that in this era of green chemistry, consider the following as a general solution, but also a green solution. Now consider taking our surfactant, one of them, putting it in water. Take a dirt cheap source of palladium, and now the interesting part comes in, where we're going to add just a pinch of borohydride. Now many of you are thinking, I know friends, you think, oh, you can add borohydride, you can't tolerate functionality, you can't have aldehydes, you can't have ketones. You already have an immediate limitation. Okay, if you're thinking that, I'll say this, not so fast. You're thinking like traditional organic chemists. What medium do you use for sodium borohydride reduction? Well, you open up Feezer and Feezer, you use methanol, ethanol, or isopropanol to slow down the decomposition. Maybe you even go to THF. Guys, we're in water. What happens when you add any borohydride to water? It decomposes. It generates hydrogen. And where's the hydrogen going to go? Well, we already know. It's going inside the nanoparticle, where our substrates are. The question we haven't answered, of course, is, where's the palladium? Well, it turns out that that cheap source of palladium, borohydride is doing double duty. It's reducing that cheap palladium to palladium nanoparticles. And this is a very interesting situation now, because we have, on the one hand, palladium nanoparticles. On the other hand, we have nanoparticles in our nanomicelles. And here comes the amazing part. If you take a picture, microscopy, transmission electron microscopy, what you will find is that you will have your palladium nanoparticles, the dark spots, which are associated, conglomerated with, or otherwise hobnobbing with the circular spherical nanomicelles. In other words, the nanomicelles, which should be evenly distributed, seek out the palladium nanoparticles. And why is that the case? Well, the answer is, if you look at the surfactant, and this is known in material science, if you have metal nanoparticles in the presence of PEG, PEG will wrap itself around the nanoparticles. So because we have a surfactant with PEG, it's a delivery mechanism. It's a beautiful thing. The nanoparticles contain the substrate. The PEG seeks out the palladium nanoparticles, delivers our substrates. That's why they aggregate. And as a result of that, here's what we can do in water at room temperature. We can take functionalized acetylenes, propargylic acetals, alcohols, protected group. How do we get protected group? We're in water. Right? Individual systems, acetates, highly prone to eliminate sorts of groups, no problem. Anybody notice the ketone in the molecule? There's no borohydride in there. Doesn't matter. Tolerates everything. It's gone. Very good yields, essentially all Z. Terminal alkynes, no problem. Notice hydrogenolizable groups such as CPC protecting group. Aryl halides, no problem. Right? Stereochemistry, untouched. Now, interesting, because remember the rules are different here. This is not traditional organic chemistry. In organic solvent, change from palladium acetate to palladium chloride, we can't stop it. It goes quantitatively all the way down to the saturated hydrocarbon. And if you ask me why that change results in that kind of a different selectivity, I'll gladly tell you. I don't know. I don't know. I don't know all the rules yet. Now, the beauty to this chemistry is also with regard to the workup. There is none. When you run a reaction in your organic solvent, what do? You throw it into water, you extract it out, you do what you do. Why would we do that? We're in water, and very little of it. So there is no workup here to these reactions. We run a reaction. When it's over, we add a minimum amount of a single organic solvent. Green organic solvent, ethyl acetate, for example. Stir it around, pull it out, all of our product comes out. The water that's left behind retains both the surfactant and the palladium nanoparticles. And we just keep going. We refresh with borohydride to get the hydrogen in there, but we're not running this under any sort of controlled conditions of pressure and all of that. No par hydrogenation, and a little bit of borohydride, and keep going. We stopped at 5 recycles, the yields are unchanged. These are the surprises waiting for us to discover with this chemistry, in this new world. Now, I could give you an explanation. I'm out of time. Right? And Fred wants to know, but you'll have to wait. Okay, so we all know that this chemistry was done by some very talented students. I don't know. I mean, this is really the work from the standpoint of the Linlaw reduction chemistry of some great students, Chris Gabriel and Eric Slack. All of the other chemistry and a lot more that you'll be reading about pretty soon, but it can't come out because it's got to go into the grant proposals to be proposed. You know how the game is played, right? So a senior grad student is going to be going to Del Bover and an off-the-charts postdoc, like the best I've ever seen anywhere. This guy is just unbelievable. He discovered all this other chemistry, the ligand, the nickel chemistry, the solutional, everything was done in that regard by Sasha Honda, who now is looking for an academic job. But the star of the show, as we all know,